right, we're gonna go ahead and get started again soon. Hope everybody had a chance to look through some of those slides on the upcoming different conferences, both this year and next year. A really cool range of different ones. Again, thank you for the speakers that have presented already. There's a really interesting mix of questions already stacking up in the questions tab. So as you type your questions there, if we don't answer that, or if they don't get answered immediately after the talk, the presenters can go in and type answers to those as well, and we'll record those questions. And actually, I think it'd be good to send out a summary of those questions following this forum.
All right, so we are ready to go on to Sarah at this time, unless Fabian has anything additional.
Nope, that's perfect. Let's go right to it.
All right, so we will get those polls sent out. So,
hello everyone. Let me change my presentation. Can everyone see my screen?
Yes, we can.
Okay. So today we have seen many processes related to bottom currents and the water masses that drive them. And right now I will show you a little bit what happens when those currents interact with a different type of currents that have been mentioned here today as well, which is gravity-driven currents, so gravitational flows. So as many of you already know this, bottom currents tend to be baroclinic flows. They can also be barotropic. But what does that mean? Well, a baroclinic flow is driven by density contrast. So its salinity and its temperature is quite different from the surrounding water masses. And you can imagine this as a plunging water mass that comes, for example, from a more constricted basin or even from the poles. And that's why it's very different, significantly different from the other water masses that are in the ocean. So when it plunges out, it will have an horizontal front, and it will have such different characteristics that it's capable of flowing around the slope and contouring at different depths. And that is why these currents are capable of not only winnowing, but also reworking and depositing sediments as well. Sorry, there is a message here. Okay, all good. But what happens when we start to deposit these systems? Well, we have seen that they have many features, both depositional and erosional. So you can see, for example, in this example, that they can create drifts with different shapes, but also erosional features such as channels, such as terraces, and others. So what ends up happening is that with the passage of a water mass during several million of years, or even thousands of years, we end up developing a contrite system. And so that system can have, as you see here in the seismic, many features within it. And here you have, for example, the terrace that you see here in this model as well, the more muddy sediment, which forms a drift, and even intercalations with other types of deposits as well. And this is all related to the energy and to the differences of the main water mass that has taken the sediment that is forming the system. But now, on the other hand, we have gravitational flows. And gravitational flows can be quite different. As most of you know, they can be cohesive flows. They can be non-cohesive. They can be laminar, which is slightly more rare, or even turbulent flows, which is the most common that you see in most systems, as is represented here in this model. They can be hyperpycnal or hypopycnal. And what that means is, for example, if they are hyperpycnal, they can be quite dense and quite heavy with the sediments when they flow down slope. If they are hypopycnal, their density is less than the surrounding water and the water that they flow through. So they will flow along in between surfaces rather than along the bottom of the seafloor. For example, in this experiment done by Snow and Sutherland, we have a representation of such a flow. And you can see here that this turbidity flow in particular is hyperpycnal because it's much denser. It flows down along the slope, and you can even see the shape of the main body, the head, and the turbulent clouds and the billows that it forms. So this is a much quicker, much faster process than the bottom currents that we saw previously. In addition, the types of systems that it forms some people might think that it may be different from contrites or somewhat more similar. But what you see is mostly that it has a source to sink system. So it has a point of entry. For example, it could be a river, such as the case here shown in the Congo Fine example from colleagues from Aspiros Azabala. And you have the river of the Congo, which provides a lot of the sediment through the Congo channel, the Congo Canyon, and then it deposits fans later on. And here you can see many of the morphologies that are formed by those flows when there is some discharge throughout. And they can be quite sinuous channels, but also you can have depositional features as well, such as those that we mentioned before. So you can have, for example, turbidite levees laterally. They are represented here in this model, or even channel lobes if it's at the end of the system and they are part of a submarine fan, so it's more complex. So you have two types of processes that occur on deep marine settings, but of course the deep marine system in a deep water environment is not a strict, is not a confined environment. So the two processes will often interact. And what happens when they interact? Well, you could have the processes interacting synchronously. For example, in this model, we have drawn here several channels along with several overbank features along this tributary network that goes towards the channels, but also you could have a bottom current that sweeps through them. And when you have the turbidity flows flowing downslope, the bottom current that is flowing throughout this area at a very specific water depth, it can take some of the sediment that is being carried, not only in the turbulent cloud, but even some of the coarser sediments could be deposited closer to the margin of the channel. In addition to all of that, you have other processes occurring. For example, if there is a lot of deposition in between the channels, so in an interchannel area, you could have very significant oversteepness. So you could create more mass transport flows or more turbiditic flows, and you could even get self-sustaining flows in this area. In addition, you have a lot of pelagic settling happening in the background, and this is even one of the most important processes because it provides a lot of the fine-grained sediments that we see, and that we see not only in mixed systems, but also contrites and turbidite systems as well. So we end up with a setting where we create features like this. We have a mixture of erosional features, several channels that could be oriented downslope, and several depositional features that you see here with less bright amplitudes. And this case is taken from Uruguay, from the Cretaceous record. In addition, you can see that a lot of the sediment that is being carried laterally also can derive from the depositional features as well. You can see that there is a collapse of the flank here, but also some of the shapes that you see here of the sediment deposition, which is related to the current pirating fine-grained particles. So it's a quite specific setting, but quite often it occurs a lot in the deep ocean. But what types of mixed systems do we really have? Well, in the past, I had the luck to be able to work with different systems, different margins, and also to talk and discuss a little bit with other colleagues that worked in other systems. And together we put up a model to represent all the different systems that we saw. And when we started to look into their variability, not only from proximal to distal, but also, for example, in the dimensions that these features have, in their orientation, and even the type of sedimentary phases that can occur in them, we realized that they could be somewhat classified. So we identified that there were systems, mixed systems in particular, that were more contrite dominated, systems that were more synchronous systems, so where the two processes are more balanced, and systems that were more turbidite dominated. And I will show you examples of each case so that you have an example to look into, and something also that you might use to discover other mixed systems when you look at your own margins. So for the first case, for contrite dominated systems, a lot of the thing that we noticed was that, for example, some of the depositional features, here you have a case in the US Atlantic margin, and a lot of people might know that this is very close and even includes part of the Chesapeake Drift. and the submarine fence and the channels that cut through it. So in this case, you have the positional features, and you can tell right away that instead of being oriented downslope, like what you see in a turbidite system, for example, they're oriented along slope and sometimes oblique. Here you can see the same thing as well. Another thing that was quite clearly noticed was that the channels that occur in contrite dominated systems are also being forced to contour around these depositional features. So that quite often they will not cut through the thickest sediment deposition that we have here, so the mounded drift, and they will also contour around. And because of this forcing of the channel geometry, you might end up with several ponded turbidites in the channel. In fact, a lot of the sediment that comes down slope could be even taken into building the mounded drifts, and that way you don't form significant submarine fans. In addition, if you look at them into the seismic line, you can tell right away that their geometry of the mounded drift is quite similar to what you see in contrite systems. So they are vertical, grading stacks. They might prograde a little bit at slope, but they do not shift laterally or down slope like you see in other cases. And this is particular for contrite dominated systems. In addition, because the current is considered stronger in these types of systems, what you will see is that more often than not, you'll probably have synchronous interactions and even phased interactions. But the synchronous interactions is mostly the bottom current, parenting a lot of the sediment. And in the phased interactions is that we still have a bottom current as well occurring in this area, while there are breaks in the turbidity flows. And that's why we end up with morphologies that are more similar to those of contrite systems. Here you have a thickness map of the same system. So this exact one, and you can see where there is a main depositional and the channels that cut through it. Now, if we go to more synchronous systems, so we are talking about cases where we think that the two processes are more balanced. So there are not so much breaks in one or the other, and one that will not have a very high or very different velocity than the other. We start to have slightly different morphologies from the previous one. The first thing that most of you will notice right away is that the morphologies are gentle, but also much smaller than before. In addition, all of them are migrating laterally towards one direction. So both the mounded drifts that you have here, these small lenticular shapes, and also the channels as well, which have less amplitude reflections than before, and also that they stretch laterally from the channel into the drift. So there's this whole pattern, this stacking pattern that occurs in these types of systems. Well, what do they look like in a map? Well, they are no longer oriented along slope or oblique. They are quite often oriented downslope. So this is the map of this exact horizon that you have here. And this case is from Nova Scotia, from one of the margins that I've worked on. And you can see that the features grow considerably in thickness in the middle, and then they lose and taper off. In addition, you will see that the channels in between follow the same orientation, but they are quite linear. So they are not as sinuous channels as we saw before. And they are not sinuous channels like you see in turbidite systems. They are quite linear, and also they become more unconfined further outward. So this is quite characteristic for them. In these systems, in addition, we will see both synchronous and phased interactions, and we can even tell this from the seismic, because, for example, this reflection here, you can see that it stretches laterally into the drift and that it loses amplitude and thickness, and that tells you that some of the sediment that was brought during the turbidity flow that deposited this one reflection was captured and transported laterally. So we had a synchronous interaction happening at this time. And that will occur throughout this type of system. But what about the other end? So the more turbidite-dominated systems. Well, as the name says, its features will be more similar to what you see in turbidite systems. So for example, you have here an example from the Weddell Sea, where you can see that you have two levees. You can see that their shape is much more cuspate. So they are no longer gently mounded. They have quite steep vertents, particularly close to the channel. And before, you only had one drift next to one channel, and then the next drift was associated to the next channel. So this is quite different because you have two levees laterally from the channel. In addition, you will see that they are oriented downslope, such as the map that is shown here. And this is another case of a turbidite-dominated mixed system, but at the present seafloor of Nova Scotia. And the most particular thing that you will notice is that one of the levees is much thicker than the other. In terms of thickness, in terms of height that it reaches, is much bigger. And this is because the bottom current not only winnows sediments being brought by these channels, so that from the turbulent clouds and distributes laterally, but also takes and reworks some of the sediments from this levee that is on the other side and deposits here. So it strips and winnows some of the sediment. In addition, you will see here that the channel no longer follows the same unilateral pattern of migration, so it does not have a clear pattern of following along as the drift used to do. No, now it's the channels and the coarser sediments in it are much more distributed because here the current is much weaker. In addition, here the turbidity flows or the gravitational flows are much more prominent, so we will have maybe coarser and maybe thicker sand deposits deposited within the channels. And in these cases, they may not stretch laterally like they do in synchronous systems or in contrarite systems. If we go towards the end of such a system, so we are still in turbidite-dominated systems, but now we are going towards the deeper part, towards the submarine fan, we can also see different types of features being formed and being affected by bottom currents, but by much weaker currents. So the currents will not affect their shape as much, but maybe they will deviate it. So here we have an example from Shenglingong that was recently submitted. And you can see that there are several entry points in this case. And you have several bright amplitudes marking the position of several lobes and the channels connected to them. You will see furthermore that a lot of the lobes that derive from this entry point over here start to be deviated towards along the slope. And this deviation is being caused by a current sweeping to this area and taking and pirating the edges of the lobes, some of the finer particles that they have around them towards the extremities and spreading them laterally. So we still have a submarine fan and lobes, we should say more specifically, that you can still see its morphology, but its morphology is being slightly deviated towards along the slope. And that tells you that you are still in a mixed system, yes, but more turbidite dominated because the lobes have not been completely reworked. So they have not disappeared from the record and they have not transformed into contrarite drifts. So you can still see their shape. But what type of deposits do we see within all of these features that I've mentioned? For example, we have several models, not only my model, but models from other people that I've mentioned here. For example, for Marco Fornesu and his colleagues in ENI, for Emiliano Muti and Carminati. And all of these people, and some of our own work and even other groups, took a look into some of the sediment cores that occur in mixed systems to understand a little bit better how the processes that form them interact and also how the deposits look like when within these systems. One of the things that we tried to do was look into the deposits that may occur within channels, but also more laterally and even more distally, to see if we saw differences in the sedimentary phases. And the first thing that we noticed, for example, when we took a look into some cores that were within the channels, we noticed that there were several phases that were more similar to what we saw, for example, in turbidite systems. So here I have some examples from my work and from other works like I mentioned. And we noticed that there were, for example, convoluted beds or tilted and very distorted beds of not only local material, but material that was deposited before. And you can tell that these more than likely correspond to slides and slumps. So we have mass transport deposits occurring in the channels. We also saw that we had phases that could have very large clasts, more rounded or more with sharper edges. and they could be very convoluted. They could be more mud supported, as the cases shown here, or they could be more class supported. So we had paraconglomerates and orthoconglomerates. So we knew that we had the brights for sure. We also saw that in some of the channels, when you had breaks from these events happening, we could have deposition of finer beds in between. So the background sedimentation, which would form amypelagites, pelagites, or in a finer chondrites, when there were no turbidite flows or gravitational flows occurring, and we could have this interaction. But when we started going more towards the depositional side, so further away from the channel, we started to see a shift in the sedimentary phases. Here I have put several examples. So for example, in the first case that we have here, we noticed that some of the coarser beds, which could have erosional bases like you see in a turbidite flow, or sharp bases as well, would have coarser grains at the bottom, but then they would fine upward, which is what we see, for example, in the turbidite model of Poma. But then they would coarsen upward again, and there would be no sharp contact in between, and then fine again. So we realized in some of these beds, for example, you can see this here again, because it's coarser here, or finer, should I say, and then it coarsens, and then it fines again. Here there were some sandstones as well, which have different characteristics. So all of this was telling us that this grain size was changing throughout the core. So no longer did we have just a single event bringing a lot of coarse material. We started to have a change in the way that the sediment was being deposited. In addition, we started to see the presence of laminations, cross laminations, like you see here, some low angle ripples as well. And even here as well, you can see several ripples occurring throughout these sediments. And this all tells us that the bottom current is most likely dominating over this area, because not only did we have the original turbidite bed, but we started to see a change in the grain size. So all these changes, so for going from finer to coarser and then finer again, seeing these structures throughout the beds was telling us that another process was starting to affect the previously deposited sediment. In addition, we started to see more the dominance of more chondrite beds. So they would have not only these laminations, but also more bioturbation would start to appear the more we were here. And there was more sorting. So we were getting into an area of a mixed system where the bottom current was more dominant. And then when we got into the more distal part of the system, so we were not only going away from the main pathway of the turbidity flows, but also away from the main core of the current, we started to understand that there was a predominance of finer particles. And this is, of course, the pelagites, the amypelagites, and even very fine chondrites that we see. And you can see that these phases are quite different from the previous one, because their contacts are more gradational, bioturbation is much more abundant, and we don't have as many structures as before. We don't have as many coarsening upward sequence or erosional bases. So we were much finer material the further outward we went from a mixed system. So we could tell that there was a change in the phases from going from the channels, so where we have axial phases, going towards the margins and the drift, and then further outward. And all of this was done thanks not only to my work, but to other authors and co-authors' work as well. Now, why is it important to study all this? Not only mixed systems, but you've seen here today as well, chondrite systems and the bottom currents associated to them, also other oceanographic processes like internal waves. All of this is important for a number of reasons. Most of you already know that chondrites can be very important because they can record and preserve the paleoceanographic changes and climates, but also there's other factors to consider as well. For example, the occurrence of submarine geohazards could be more propense to occur in these systems in case there is more sediment accumulation. For example, we should consider the fact that they are also important for deep marine ecosystems, because these currents could bring oxygen and other factors that are important for the macrofauna, but also for the economic potential, the carbon cycle, microplastics, and much more. In fact, during the last couple of years, I've heard many other factors to consider and many other applications for mixed systems than the ones that are mentioned here. But since we only have a very short time, I will focus on the first 4, and just to give you a couple of examples for each one. So first and foremost, most people that study contrite systems, of course, study them in principle because they can tell us a lot about a continental margin and its deposits, but also about the paleoceanography of that margin. Here we have an example from the Antarctic Peninsula. You can see here the slope, even some of the islands that are near the Antarctic Peninsula. And further downwards in the continental rise, you can see several drifts here and several tributary networks that go into deeper depressions, which are the channels that are in between all of these drifts. I put here a line that crosses right through this drift that you can see here. And you can see that there is a very thick sediment accumulation occurring here. In addition, you can see that this sediment accumulation, so the amplitudes of the seismic that you see here, has a pattern. You see that there are darker reflections, then lighter, then darker, then lighter, then darker, then lighter. And even at smaller scales, we see the same again. So there is a cyclicity. And this cyclicity is not by mistake, actually. When we took a look into the core that crosses through this sediment drift, so site 1096, and we compared its ages to the patterns that we see in the seismic, we realize that these patterns can be correlated to the marine isotopic changes. So to the changes between cold periods, marked here in purple or dark blue, we could say, and marine isotopic stages, marked here in this more greenish color. And you can see that the patterns, which were darker, lighter, correspond exactly to these changes that we have here. So we knew that the deposition of these sediments, so the process that drives the deposition, is tied to climatic changes. And we even look into the eccentricity, the obliquity, and the precession, and we realize that there is a very tight link to the eccentricity and to the pattern that it corresponds to. So because it is in the Antarctic margin, and because this is in the southern pole, a lot of the currents that sweep through this area are actually cold currents. And what does that mean? It means that they are stronger when we have glacial cycles, because we have more sea ice forming over in the areas closer to the shelf. And the currents then, the water mass that is associated to these currents, it becomes much denser, because the sea ice, when it is formed, then you have the water mass below much denser being formed, and it descends. And so during the periods, which are glacial periods, we will have more cyclic deposition at that time. When we look into one of the cores, so we took a look into, if I'm not mistaken, core 18, which is, I think, around here, may not be represented in the figure, I don't see it at the moment, but it's around here. So it's in the extremity of the drift. And we compare some of the ratios of the elements. So we have here, for example, zirconium aluminium. You can see it's between 0 and 2.5 meters. We noticed right away that some of the coarser beds were occurring in certain intervals. And I've highlighted here the intervals on purpose already, and compared them to the marine isotopic stages through dating. We realized right away that the coarser beds, so not only the turbidites, but also the reward turbidites and the chondrites, were occurring during glacial periods. And then we had much finer hemipelagic sediments occurring in between. And this is because during glacial cycles is when the current was stronger. So that's when it was more capable of pirating and reworking the sediments laterally throughout the margin. So there's a very strong link to the climate in this case in particular. But climate is not the only thing why we look into these systems. A lot of people that look into mixed systems and even in contrite systems also consider their potential for submarine geohazards. As you know, there are a lot of underwater cables, submarine cables, and other infrastructure throughout the ocean, for example, wind farms and other things along the shallow shelf, which are affected by some of the processes that form mixed systems and contrite systems. So here we have an example of such a system, and this is in Brazil, published not that long ago, where we can see that the continental margin on this side is much more gradual and more gentle, and it has some scours that follow along the bathymetry, while on the other side, we have a much more rough topography, cut by several furrows, and which become channels. So there's a very big dendritic network on this side, and which then flows towards and forms several submarine vents. So here, where we have the interaction between these two, we have a mixed system occurring. And you can see right away that the presence of these downslope flows, but also the alongslope flows, causes a lot of erosional features. And all of these features can be very significant for the presence of submarine geohazards, and to take that into consideration. In addition, most of you know, for example, that contrite systems, such as the ones that are formed in the US Atlantic, and even for some of the mixed systems that we have in this area, they are often associated to a very steep slope, and that very steep slope has a gradient and an oversteepness that could generate more geohazards in the area. Here in this work that was done a couple of years ago, they marked the presence of several landslide scars that you can see here in red, but also the size of the mass transport deposits that are associated to them. And you can see that they are quite recurrent throughout the area. In addition, the more sediment that we put into these systems, in particular under-consolidated sediments, which can get to very big thickness and which can have a lot of water in the pore content, it could generate more slope failure, because you are putting, you are creating a significant thickness and a significant gradient over these slopes. So contrites themselves, the sediment itself, can also aid in the generation of slope failure. Now, bottom currents are not just something that erodes sediment and rewards sediment. They also have a lot of properties that are good for deep marine ecosystems. For example, contrite currents could bring nutrients, they could bring oxygen, which would be very good for the organisms and the macrofauna that exists in the deep oceans. Here we have a drawing of the different trade fossils that can be made by such macrofauna in the deep ocean, and you can see that they can vary significantly from more proximal to more distally, and even in the different types of deep water systems that we have. For example, there was a case study done in the Gulf of Cadiz, where you have several ridges and even several mud volcanoes, where they studied the presence of macrofauna, so the different types of organisms that you can have in these systems. And they discovered that there was a lot of corals and even cold water corals being formed throughout these areas. Here we have some examples. You can see, for example, many deep water cold corals, but also sea anemones, sea stars, sponges, and many other types of organisms that occur throughout these systems. So the currents not only pirate and winnow sediment, but they also bring nutrients that are very important for the macrofauna and the benthic organisms that are in this area. In addition, they can bring organic matter. For example, in this case here, they studied the presence of organic matter in proximal to distal settings, and they realized that in more proximal settings, the current would bring more organic matter, and also it would be buried much quicker. So the organisms and the trace fossils would be much shallower, while in this case, which was much more distally in the ocean, there would be less, and it would be more propense for deeper organisms to burrow and to create their trace fossils. So there is a variation depending on where the core of the current is and where it reaches the properties and the characteristics that it brings. Now, finally, most of you that work in industry know that there is an important economic potential for these systems. For example, not only for hydrocarbon exploration, but also for carbon capture and storage, and even for the discovery of mineral deposits, such as phosphate-rich sediments or iron manganese nodules. This economic potential was already starting to be discovered when they realized that there were some beds in contract systems or mixed systems that had oil or condensates in them. For example, the case of Southwest Brazil, that some of you may be familiar with. But it was really propelled forward when Marco Fonesso and his colleagues published a paper in 2020 on the Mozambique margin. And in this paper, they revealed that in a mixed system, in particular in the coarser beds that occur in this mixed system, a lot of sand was being deposited. So they had over 100 meters of sand. You can see here in the logs how thick the beds were being deposited. But also they realized that all of the finds in this system were taken laterally and pirated by the bottom current. Hence why they had such thick sand beds accumulating here in this area. So the occurrence of the two processes together, not just one, created a very good reservoir, a very good gas reservoir, which is known as the Coral and the Mamba fields. And they had a very impressive net to gross ratio. So almost, I think, 92% was the results that they got from the course. In addition, they even did simulation to check where the coarser beds were and where they were less coarse, and they realized that this high net to gross body would occur along a channel, but that laterally, a lot of the finds were pirated away. So the occurrence of the two processes was very significant for hydrocarbon exploration. But this is not seen just in this example that I've shown you here. In fact, there are other cases, like the one shown here from Uruguay, which I showed you at the beginning, which also have very high amplitude reflections within their channels, and which correlate quite well to the high amplitude reflections that we see here in this case. So more than likely, we have a lot of coarser sediments being deposited in the channel, and by having a current sweeping through and pirating the finds away and depositing it in interchannels, we might be creating a potential play here, which could be very significant. And that is why I was showing a little bit of the implications, just to present you a little bit of mixed systems and the work that we have done. Thank you.
Hey, Sarah, thank you. That was a fantastic talk. I know I have a few questions. I'm going to post them in the chat because I'm going to try and keep us on schedule. I'm going to have us jump to Christoph. Please go ahead. But again, anyone that's got questions, please add them in the chat because all the presenters can go back in and address them at any time.
Hi. So thanks for inviting us to present. Basically, we'll follow a little bit what Sarah was mentioning, also with the previous talk, and the implication with regard to oil and gas exploration, but as well the implication for understanding paleoclimate and paleocean circulation with regard to plate tectonics. So this work is mainly on the Norwegian Sea and was done at my time with AKBP, and I would like to thank them for sharing the result of this multi-year study on the Norwegian continental margin. So for the one who are not too familiar with the Norwegian continental shelf, we have three different areas. To the north, we have the Barents Sea, in the center, the Norwegian Sea, and in the south, we have the North Sea. As you see in the creaming curve, there is a lot of exploration in the North Sea with a lot of oil that has been discovered, followed by the Norwegian Sea and the Barents Sea. And at the moment, there is an effort to try to find more resources, especially in areas that are less explored, like the Barents Sea and the Norwegian Sea. and potentially in stratigraphic traps. So let's see if I put the pointer. Yeah. So this is in mid-Norway. So in mid-Norway, the main resources are being explored in the Jurassic Play. But on the way down, when they were drilling in the early 80s, they start to realize they had a lot of Cretaceous sand throughout at different level, from Appian Albion all the way to the Maastrichtian, or like the boundary with the Tertiary in the Paleocene. So we will focus only on the Cretaceous today. So here you can actually see the stratigraphic column where you have some long sand in the Appian Albion, and then Cenomanian, Turonian, and then in the coniation you have the Lucene. So in this area, a lot of fields have been discovered, and some quite large discovery. So you have the Alfield discovery in 2000, about 300 million barrels of oil recoverable, and about 50 to 60 kilometers long along the Paleo slope. And then in other places, you have four-way closure, like the Ormelang field with almost 600 million barrels of oil equivalent. So through time, the exploration started in early 80s, 81 until now. So it's about 45 years of exploration. So there is a few wells drilled in the early 80s, and then they were visited and trying to understand the depositional environment, how would they distribute, what is the quality, and how we find stratigraphic traps. So Shannon Lam came to Norway to describe a lot of the core along the Norwegian continental margin, and he started to notice there was some mass transport and then the effect of some bottom current. But afterward, a lot of the explanation for those Cretaceous sand were related to turbidite system filling in some of the rift morphology in the basins around, as you see in all those different cartoons all the way to 2021. So at the same time, after the discovery of the Hadfield field, which is this elongated amplitude, so this soft represent the gas field, and then there is sand throughout the area, and this is the contact about this point. If you go up dip, you have a lateral pinch out for about, as I said, 50 kilometers. So a lot of questions were, how do we form those stratigraphic traps, and what are the processes controlling this type of large stratigraphic traps? So there was a lot of work done with Stirling, the edge of the wedge, and trying to see the link between the paleotopography of the rift and the way the turbidite were deposited in the basin. But as you have seen now over the last few talks, there is a lot of discussion with regard to mixed system in deep water system. And recently there was this sand detachment, maybe analog for stratigraphic traps, and then we have all the shallow marine system. But then when we get on top on the slope or in the basin floor, we have, of course, the turbiditic system that has been quite successful in the past. And then there is some hints with the class 3, with the contrary deposition in the center of the basin, as Sarah mentioned now, with some of the cases in Mozambique or Tanzania. And then we also have the contour current erosion that could actually make the sand to be detached from the feeder system, like in the picture A here. So if we start to think about the model with gravity deposits developed by Exxon and other companies, we get to see those deep water systems where you have the canyon, the channel lobe, and then the distal fan system. But with the work from Fenoso, we start to see that there could be a full mix of spectrum of system, with well-defined, wind out of the way, where some of the coarser sand can actually be remobilized and form those dunes or sheets. And then in other places where you have muddy contrite drift, controlling the paleobathymetry and the deposition of the turbulence. So with that in mind, we tried to explore the Norwegian continental shelf, but by getting a better perspective, by integrating a lot of data. Usually we see a lot of the core, and we try to, like Kevin mentioned, trying to find key criteria to differentiate turbidite or chondrite. But the idea here was to make the full use of the seismic data that is available in Norway, with almost 3D data covering the entire shelf, and not only doing seismic stratigraphy, but looking at the seismic geomorphology. So we are very lucky to work in Norway. It's fairly mature area, and there is a lot of 3D data. For example, this survey from TGS, which is the Pure, it's about 45,000 square kilometers, extending 400 kilometers of the margin. So how do we target those very large cube, and how can we actually tease the detail to help us making the connection from basin scale almost to core scale? So there's a traditional approach, mapping with Petrel, and then the use of PaleoScan and integration with geoteric. And then one of the main turning point is trying to look at modern and ancient analog that is also supported by the drifter, as we have seen with Sarah, and then later on Javier, who will be presenting some of their work. This is very inspiring, trying to better get a picture of the complexity of those deep water systems. So we will go through 3 cases, one in the Vestfjorden Basin in the north of the mid-Norway, one on the Donna Terrace, and one in the Mølle. So we will start with the Lange, Lysing, and then up into the Maastrichtian with the Springer formation. So in the Vestfjorden, this was one of the first wells that was drilled in the early 80s, and you can see not many wells on the Donna and Alten Terrace. And there, Shannon Graham started to realize there was some event associated with bottom current and interaction with mass transport. So this is located in the north here, and here you have the base Cretaceous. Just to give an idea, you have a series of highs with the Grønne High, the Røde High, Sør High, and then you have some ridges outboard, like the Sklina ridges, and all those amplitude here are related to those Cretaceous system, where in some places you see the canyon, and then you find all those interesting morphology down here. We will dive into more detail. So in the northern part, you have the Grønne High, and then you can actually map a lot of the canyons coming down, and then you have the basin. And here you can actually map the base of the BCU, which is represented on the map, and then the full Cretaceous sequence, where you see all those overlapping packages, and in some places thickening towards the slope. In that case, they drilled a well, they found a lot of sand throughout the Tertiary and the Cretaceous. They were deposited as, or interpreted as turbiditic fan. So now if we start to link what we can see in seismic geomorphology with the well and the core. So in this case, the well is located up here, and then we start to see that we have the active canyons in red, and then some of the canyons were not providing a lot of sediment, but the southern one, and then you can actually map those deep water systems going to the north east into the basin. But we also see those sort of elongated systems. But when we look in the core, we find all those conglomerates, and then those massive, mainly turbiditic system. If we go up into the level just above, we start to see that there is a new canyon that is being activated, and we see all those very nice channel system coming out and then being deposited into the basin. But then in this area of the well 3-1, we start to see all those elongated. And here we see a big difference with the sedimentary facies. We see all those cross-bedded, glauconitic, highly biotubated system, and a repetition of those. Those have been interpreted to be either low density turbidite or reworked by bottom current. If we go to the interval just above, in the coniation, then we don't see any of the gravity processes coming down into the basin. We see all those along slope systems. So we have an evolution from downslope in the lower part of the Cretaceous and then up in the stratigraphic sequence with more along slope processes. Now, if we move to the Donut Terrace, just to the south, there was the Alfield discovery, which is this elongated field with a stratigraphic pinch out towards the edge of the Newland Ridge. And then at the time, they had little patches of seismic and trying to do this seismic geomorphology connecting to the core. And then other models were showing axial and system coming down into the basin. But throughout those studies, there is always something that is coming back, is the presence of those enigmatic facies. And those enigmatic facies have been published in a lot of different period of time. So Shannongham in '94 were describing those as tidally influenced deposit, maybe estuarine with those crossbeds. Later on, they were interpreted as traction currents. And then recently, they were interpreted as either upper delta front or cross-stratified with the channel lobe transition. So we see we have a full spectrum of deposits, and as Kevin mentioned, sometimes it can be challenging to find out the deposition element from just the core. So let's see how we can actually do this with the help of seismic data. But before we move on, it's quite important to understand the processes, because all those cross stratified sandstone, if you actually look at the reservoir property, they're usually above 1 Darcy, and in some places up to 40 Darcys. And then the facies 2, L2 here, you see all this dewatering, and then those are massive sand with dewatered. You have the same range of porosity, but the permeability are a lot lower. And then the same when you get down into those rippled and laminated sandstones. So how can we actually predict and link what we see in the core with what we see in the seismic? So when it comes to seismic, there's been a lot of improvement in the Norwegian Sea from, if you look at data before 2007 to data after 2017, you start to see a lot more definition in the Cretaceous. And then you start to see the field here with the pinch out here, and then you see those little blips of amplitude appear. So if we start to look at the level of the Alfield field, where there is this discovery with about 300 million barrels of oil equivalent, which is mainly gas and condensate, you start to see the pinch out, and then you see the response on the gas. But then in other places, we start to see some features. And if we go to the next slide, when you actually do the detailed seismic interpretation, you start to see all those elongated ribbons or furrows. So this is something interesting at the level. But maybe the seismic quality or the thickness of the sound doesn't allow us to see any geomorphology in this area. So let's move just one slice below. And then if we take the one just below, now we are in the Lange formation, which is just lithology definition. But we get to see that we have some features appear, which are those on the pinch out. We have those elongated anomalies, and then they are drilled in some places, and we know that we have sand, so there could be elongated dunes, a little bit what we found in the Oligocene system in Brazil with the work from Petrobras and by Muti in 2014. And then in other places in the basin down here, we get to see some of those crescent shape, maybe bark and dune encased in mudstone. So we are lucky in that case is that we have maybe thin sands and encased in mudstone with a little bit of gas, and it allows us to see this seismic geomorphology. Then if we move further south, we can go into the Meuse Basin with the Froan Basin, and this is the Olmelange field. So the Olmelange field is this very thick package of sand. So to do that, again, is to always good to make the full use of the 3D data available. In this image, you have a surface almost extending 250 kilometers. Here, outlined in dashed white, you have the Olmelange field, but we will focus mainly on the edge of the basin here, in this Upper Cretaceous Paleocene elongated mound on the edge of the Froan Basin. But if you look here, you have something very similar up here. So when we look at the seismic line in the area up here, you can actually start to see this little blip or this little mound on the seismic data at the transition between the Upper Cretaceous to Lower Paleocene. So if we make some section throughout, so if we take a section along the dip, you start to see this mounded sort of geometry and pinching out as you go south. And then you start to see this erosional moat potentially in the area. If we take one along the axis of the system, you start to see all those shingles downlapping and then pinching out as you go to the north. And this is about 45 kilometers from this end all the way to the tail end of this mounded features. And we don't have much time now, and the seismic quality is not good enough, but we can actually start to notice all those deep water channel system coming down the slope here. So if we start to map in detail, we can actually see a lot of different units. So we have the unit 1, which is this channel system with those finger-like features. Then you have the unit 2, which is the elongated one that goes about 45 kilometers. And then you start to form this unit 3, and you see the orientation of this mounded feature is slightly changing. One of the things to notice on this RGB blend is that we have this highly polygonal faulted interval. And then when we go towards these mounded features, we lose the polygonal faults, and then the frequency content is changing, most likely associated with lithology. And right on the edge, you start to see those zebra type features, and maybe here some elongated features. So if we do a zoom in and we look into this part, we start to see a lot of, on this seismic inset, a lot of scours formed, and those scours have this almost north-south orientation. And then as you go to the north, you start to see those dune forming, which what we see on the spectral decomposition RGB blend appear. And then the polygonal faults. If we look now on those zebra features, we can interpret them as sort of sediment waves along the basin. And then by using different attributes from the proximal to distal, we can actually see they are elongated along the axis of the very large drift. So when we look at the concept, a little bit what Sarah was mentioning with proximal to distal with regard to the contourized system, a long slope process, and proximal to distal with regard to the turbidites, we start to look at all those different features with the polygonal fold, the sediment waves, the mounded elongated features, the dunes and the scours. So we start to see the effect of bottom current modifying the turbiditic system coming down into the basin. So one of the things that we have noticed is that revisiting all this data and history of exploration in the basin, but with the use of the 3D seismic data that allows us to actually dive into the detail, allowed us to get a better picture of what's happening at the basin scale, but also how it's helping us to understand the reservoir property, the mechanism for forming stratigraphic traps into the basin. And this has implication for future exploration, either opening new ideas and developing new play concept in a relatively mature shelf. It can also help us to bring additional smaller interval into production very close to infrastructure. And then with regard to production, allowing us to better understand the 4D response and drilling infill wells and so on. So this is the main application here that I presented is for oil and gas exploration, but then there is a lot more implication with regard to paleocean circulation, paleobasin morphology, and also the different water masses in response to opening and closing of the North Atlantic and the Norwegian Seaway. So with that, I would like to thank again AKBP for allowing me to present some of those images and part of this multi-year regional studies, and also TGS for permission to display some of the seismic line from the multi-client seismic, and Vår Energy for supporting my participation at the forum. Thank you.
Well, Christophe, that was a great presentation, and I'm sure everybody was blown away by the imagery. That is phenomenal imagery. Again, I have a bunch of questions, and I'm sure others do, so please add your questions in there. For the sake of time, let's jump to Javier now. But again, what we'll try and do is, as Javier finishes, we'll try and preserve some time for a few more questions there again. But please add your questions in the chat. Thank you.
Hello everyone. Can you hear me and see the presentation?
Yes, we can.
Okay, thank you. Well, first of all, thank you for the invitation to be involved in the forum. And I know it's late, and it will try to be quicker and simple today. And one of the beauty to be the last, that you can see the question in the chat and see what people is, taking from the previous speaker. So I will use also that during my presentation. And the presentation today is mainly about contract, really, because Sarah was more in the mixed system. So it's contract depositional system, paradigm for the water sedimentary environment. So this is the outline for the talk, an introduction, review some diagnostic criteria based on seismic, sedimentary facies, logging, and something about sandy versus muddy contracts. Then I will go quickly into the implication and then go into the future consideration. So my talk is mainly focused for those that are less familiar with the topic and for the non-believer. That means people that know the topic, but they are not completely convinced about the importance of the deposits in the water and in the exploration in the water. So going to the introduction, contracts started in the 60s with the pioneer like Hessen in 1966, and other authors that recognize ripples and bedford in the very deep water and started to relate the bedford with oceanic circulation, and also using a monochannel high resolution signal line, and started to identify morphologies that they were by that time completely new for the community. But since then, during the 80s and also during the 90s, the main focus on contract was to try to classify this deposit into the deep water environments and also to try to go into the cementological characteristics of these deposits. And then later, from the 90s to, I would say, 2010, researchers started to integrate morphological, cementological, and seismic facies in the characterization of these deposits. And since then, 2010 to today, I would say, there are a completely explosion of groups and research projects about the topic. And all the results from this new research were in new research lines like immunophages or microphages or the clinical characteristics of contourites, and also try to do experiment on numerical modeling, monitoring the mother ocean in order to understand more the processes and to understand more the deposits. So I think we are now in that phase, but including also today new processing techniques, machine learning methods, and AI to characterize this deposit. So we are now there, but it's an authentic evolution in the topic so far. So contourites. It's interesting because my experience during the last 10 years, I would say that in academia, but mainly in industry, that still people assume that the deep water environment is very quiet. I have seen some question in the chat that is linking to this comment. So maybe it's because the formal definition from contourites, because the formal definition from contourites in the 60s was that contourites are those sediments due to the influence of thermaline currents. And here you can see the modern day global oceanic circulation, the thermaline system. That is very weak in general. The average is less than 5 centimeters per second. When you go to the western side of the oceans, of the marine basin, it's higher, it could be 10 to 20 centimeters per second. But again, it's very weak. So we all assume that the deep water is weak in terms of energy, and these kind of deposits are therefore fine-grained sediments. And it's not possible to have coarser, gravel, or sandier contourites because the influence of the oceanic circulation. But there is something interesting that don't really consider, or we don't really consider much of the time, that we normally speak about water masses and current. We don't really differentiate these two terms, because water masses is a body of water with physical properties. It's defined by physical properties. Normally we simplify in surface, intermediate, and deep, but it's more complex than that, because in some ocean we have today, for example, 6 or 7 water masses. For example, here in the Southern Ocean, you can see from this work from this author, different water masses, surface, intermediate, and deep in this part of the ocean. And all these water masses are important in shaping the morphology of the seafloor. And then we have currents. But currents is not because of physical properties, because the movement of the water. Because different processes, could be the wind, could be Coriolis, could be cabling, and other, potential processes. So basically, I want to say that the two concepts are different. One is function of the physical or chemical properties, and the second is a function of the speed. In the short term, it's important. When we are talking in geological term, in the long term, the two concepts are, associated in a more closer way. But what about the modern day definition, or the definition that we are using at the present? So we use the concept of contourite for those deposits that have been deposited or substantially reworked by the persistent action of bottom currents. We don't use benthic current, we use bottom currents. And this is a definition from Doristo and Revesco in different publications. So here you can see bottom currents in the Northwest Pacific Ocean in around 700 meters. By the way, the facies are very sandy. Why we consider bottom current? Because the definition for bottom current that we use is that they are semi-permanent water masses flows with the capacity of the load transport for depositing sediment on the seafloor. So it's not anymore thermaline currents or thermaline system in the definition. And the reason is because there are other processes, as Elda and Sarah and others today explained before. So there are a number of secondary oceanographic processes like internal waves, internal tides, eddies, etc., enhanced or modifying the background, the geostrophic current, the thermaline system. And most of these secondary processes are very energetic. And some of them, the velocity associated with this secondary process could be more than 100 centimeters per second, much more higher compared to the thermaline circulation. And with this velocity, because the influence of these secondary processes, we could have coarse sands or even gravels in the deep water because the influence of these processes. Therefore, my main message for this introduction is that the deep marine basins don't exactly represent the weak, low energy sediment-starved environment that traditionally is assumed. And here in this figure, you can see the distribution of the bottom currents globally. And in yellow and red, you can see the area with higher velocity. You can see that maybe along the lower slope, continental heights, and because the interaction of this thermaline system and these secondary processes with the irregularities, the velocities could be very, very high, more than 100 centimeters per second in many areas. That is why the influence of oceanic circulation, and that is why we could have in the deep water sanitary system pure gravitational system, for example, fluid system. We could have when the currents and oceanographic processes are dominant pure water system, because the interaction of the two, as Sarah explained very well before, mixed systems, and also in areas with less influence, hemipelagic or pelagic deposits. But the reality is that all the systems interact laterally and vertically all the time. So what are the criteria of the main ones? So normally we use drift for the larger bodies of sediment affected by water masses and bottom current. This is a drift that was, this is a drift from the South China Sea, and the term was defined in the 60s for Hessen and Johnson in this fantastic book, The Face of the Deep. And there is different type of drift. 9 type of drift are considered in the literature. Probably there are more, that they are less known, but we all assume that at least there are 9 type of drifts. So what does mean? That in a contrast system, we could have a great variety of drift, not only Mount drift, but also we can see, because the influence of bottom current, other features. As a more erosional, they are mixed. And this is important because we can see, as I said, the positional feature, for example, a drift, erosional feature, for example, channel or MOAD, because they are different concepts. We can see erosional surface, or we can see what we call mixed feature. It's not a mixed system, it's mixed feature because the processes are changing on time, and sometimes some features are more depositional and then changing for erosional. And that is why it mixed. But the reality is that all of the features, laterally and vertically, are together, forming what we call a contour depositional system. That is a concept similar to, for example, turbidite depositional system. But it doesn't mean that all the deposits on the drift or in the erosional element necessarily are contouritic. The reality is that on this drift, we could have turbidite, we could have reworked turbidite, we have mass transport deposits, fine-grained contrast, quartz-grained contrast, and others, as we see in pure gravitational systems. So there is a variety of sediment, and something that we hypothesize, because it's a working hypothesis, that these contrast depositional systems are linking to one particular water mass. For example, here you have water mass 1, water mass 2, and there is an interface or a transitional zone between the two water masses. So the drift, the depositional element, or you allow me to say the main deposit of sediment is with the energy is minimum. So not necessarily when you have a stronger current, you have more sedimentation. In fact, it's the opposite. The main deposition is where the currents are weaker. When you move laterally to the position of the currents, of the core of the current, is where you have more erosion. And in those settings in which you should expect to have coarser sediment. For example, in this example, I included in yellow the potential location of for sandier deposits, and then in green, more fine-grained sediments. So the thing is that all these quartz sediments are here because of gravity, but then laterally affected by the water masses and also by the secondary processes. For example, in these interfaces are the key areas for the influence of the internal wave that was explained before, the internal tides, or the processes. So these areas are really depths in the ocean which there is maximum energy and which the process have more capacity of transporting and eroding sediments, or water sediments. What about the criteria? Here you have this nice example from Newfoundland, and there is some basic criteria. For example, drifts in general are parallel to the margin, parallel to the irregularities. Internally, there is a upslope or upper relief migration of the deposits, but they are other. Normally, there is a key or basal surface that usually is an erosional surface. There is internal discontinuities that normally represent also internal erosional surfaces. There is non-stratigraphic conformity between the top surface of the drift with internal layer, and there is a hierarchy of high to low deposits when you are from the core position laterally in the drift, but also up current to dock current. So the variability is in 2 dimensions, not only in 1. Normally, in this kind of system, there is different steps in the evolution of the system, starting for the onset, and normally is characterized by fabular drift or shitty drift, and then evolving to the growing phase that normally is among it's a general assumption because it's not that simple, but let's say that by now. And how to identify this, or how to develop a seismic analysis of these deposits? What are the criteria? Normally, we study this system at different scales. In a large scale, try to identify the larger feature that we call the third order feature, and then we go into the subunits to the medium scale to see the stacking pattern of the deposits, and then we go into more detail in the third order level to identify the seismic phases of bed form within the subunits. So there is a hierarchy in the way we do the seismic analysis to characterize these deposits. Normally, the drift and the contour system are huge because they are associated to water masses. For example, today the Antarctic bottom water mass is flowing all the oceans, the southern hemisphere and in the northern hemisphere. And associated to this water mass, we have laterally, time to time, huge drift. So these drifts are in a basin scale. They are not local. They are even larger than the gravitational system. So what is happening to identify this drift is you are working in regional 2D seismic line. It's even easier than if you are working in 3D seismic data. So you cannot really see the dimension of the feature. So if you are going to identify this drift, I would suggest to see first the regional 2D seismic line and then go into the detail of the feature with the 3D seismic data. Here you have in this sketch from Adam Kirby the different steps onset and growing. Some people consider also a maintained stage at the end. And for example, the drift is a third order. The channels or moats or terraces are also third order because they are very large. And as a second order feature, you could have erosional surface or small terraces, scar, furrows, scar gullies, and so on. Or sediment wave or other bed form or mastrapo deposits, channel overland deposits to be identified, etc. So they are smaller in scale compared to the freshwater. In terms of reflectivity, we know relatively well where the high amplitude anomalies are associated to the different drift, to the 9 types of drift I mentioned before. So we know that mainly the high amplitude anomalies in seismic 2D or especially in 3D are within the channel associated to the terraces or in front of the gateways or straits. An example of this secondary feature are, as I said, sediment wave. Here you have a nice example from Hanford, from Tennessee. And you can see perhaps here the morphology of sediment wave. Here another example of sediment wave in plan view from the Cretaceous in Namibia, where you can see a submarine canyon from there to here, crossing the margin. And then laterally you see you have these wavy facies that they are sediment wave. And the interesting thing of this example is this: there is sandy deposits or sandier deposits with high amplitude anomalies between the wave crests, initially linking to the sediment supply through the canyons and then reworked by bottom currents laterally. Another example, there are these sandy ribbons from Norway, or a secondary feature of these amazing sandy dunes and furrows, as well from the Norwegian margin that you can see here on the right. So these secondary features are very common, and with the 3D is a fantastic tool to identify this smaller feature, very indicative of the influence of these bottom currents. In terms of sedimentary facies, there is a great variety of facies, depending on the velocity associated to the bottom currents. Here you can see in red the threshold velocities from hemipelagic to muddy contour or from muddy contour to sandy contour, and then with more than 80 centimeters per second, the possibility to have erosion in the seafloor. This is mainly for siliciclastic components, and we have to consider when we have more bioclast component, the velocity are weaker. For example, to have calcareous or sandy or sandy or sandy deposit composed by bioclast, the velocities could be not 20 centimeters per second, could be only 15 centimeters per second, because the hydrodynamic behavior of the class is, different compared to the density compared to the siliciclastic particles. In terms of the sedimentary facies, we all assume a model for contours that is mainly working in fine-grained contours. And this is that we call the bigradational sequence that initially was defined by Gontier et al. In 1984 in the Wool of Cadiz, the south of Portugal, and then refined it and changed it a bit by Dogenstow and Jean-Claude Fourier in 2008. So this is the typical sequence of facies for contours, where sediment fine-grained contours are evolving to sandier in the central part, and then quartzing hour, and then final hour in the top, from sandier to muddier again in the upper part. That is why the degradation trend in the second. In logging, for example, these sequences could be identified using gamma ray, with a lower gamma ray in the central part and higher in the lower and the top part. And density, velocity, and resistivity logs will be also useful to identify this asymmetric variation for these conductive deposits. But this second of phases is very common and it's mainly on drift. It's not in the channel, it's not in the front of the channels, it's not in the terraces, it's mainly in where you have the main deposit on the drift. And when you move distally, you can still see the variational sequences, but thinner. The variational sequences, the average is around a meter or half a meter, but we have seen a variational sequence with more than 10 meters in some areas, or even thinner. And when you move distally, the thickness of this variational sequence is very, very thin. When you go proximal in the system, you started to see asymmetric sequences, and the top part is eroded away, especially on terraces. Another thing is the deposits, the sanded deposits in the erosional elements, mainly within the channel or in the mixed element, mainly on the terrace. These are the areas where you can identify in environment dominated by bottom current quartz sediment. You can see gravel, you can see quartz sand or fine grained sands in this environment. The thing is that so far there is not a sedimentary facies model for the sand deposits. Have been studied by different authors, but still we have not a model for these quartz deposits. And then here in these proximal areas, we could have reworker tubidites, we have proper tubidites, and distally perhaps pelagic and pelagic, and that's the normal. Within a system, within a contrast system, we have laterally and vertically the association of all these facies. That is why it's not simple to identify this deposit on the field. And that is why it's not simple to identify this deposit when you have a well, when you are working with logging data. Here you have an example of sandy deposits in around 1,000 meters in Southwest Pacific. This is a video from a recent paper from Shannon Frey, sorry, and you can see this deposit affected by bottom currents, and the scour of the current interacting with these blocks and irregularity. There are a number of examples where people identify sedimentary facies. And there is some analog, good analog in the field to see pure contourized facies. For example, Cyprus or Morocco or California could be more reworked, or different areas, Angola, for example, where some different authors propose facies for these fine grain and quartz grain contours. I selected two to show you very quickly. One is from Cyprus that we have been working for years here. And here you have an example from the field, from an outcrop. This is middle Miocene in age of these variational sequences. So let me use this name that I know they are not so well considered at the moment. Cancellotite on the lower part, calcarenite in the central part, and then cancellotite again in the upper part. But it's quite interesting because you can see also that the thickness of the layer is changing. It's thinner in the lower part, is thicker in the central part, and becomes thinner again in the top. So it's not that simple that it's changing for quartz and therefore finer. There is some internal variability producing that we call layering or banding, and this variation in the thickness of the beds. So all are criteria to identify contrast and declarational sequences on the field or using cores in a well. So many evidence of reworking, interruption of sedimentation, that is the key to have these, let's say, sandier deposits. When you see the microphases of these calcarenites, in this case is more carbonate, and it's mainly containing up to 98% of forames, especially in that we call the non-compacted layer, that's the more endurance layer here in the sample. In Caravaca, Murcia is even better because we can see a complete sequence of deposits in a drift. And normally, the long-term variation of grain size is quartz in hour. So it's finer sediment in the base. You remember it was more tabular in seismic, but when you go in the growing phase and at the end of the drift, you have quartz sediment. So that means that the lower part of the sequence, you can see fine grain vibrational sequences and contours. When you go in the middle part, you started to see more quartz contours with these vibrational sequences, not very different to the sample I showed you from Cyprus. In the other part, but when you go to the upper part of the sequence, you start to see something different. And here you can see proper sandy contours and a lot of reworked turbidites. So this is very common, and it's interesting because at the end of the day, when you are working with seismic, you are in the field, that you can learn from this long-term variation is that the current is weaker at the beginning and enhancing all the time up to the top of the drift, and then stopping. And that is why you have a lot of reworking at the top of the sequences. And most of the time, they are initially, usually, turbidites or master of deposit being completely reworked or partially reworked by the bottom currents. In this example, for example, on the top, you can see a scour at the base of the turbidity layer, and then the internal deposit on the base deviated completely to the turbidity. What does mean? That initially the deposits were there because the turbidity flow, and then, as I said, it worked. And this is a nice example of what I try to say here for the Norwegian margin, where you can see these gullies or canyon, and at the end of them, you can see a submarine fan, but all the submarine fans are deviated by the action of the bottom current. In a more extreme situation, like this example from Bernelle, from Brazil, you can see the gullies on the slope, and then you can even not identify the fan because have been fully, completely reworked by the action of the bottom current. And the reason you can see now is the sandy deposit developing these sandy ribbons along the margin, parallel to the margin. So finally, implication and future consideration. I am very close to the end now. Implication, you heard many in the previous talk. I'm going to simplify now this for you. So many investing analysis. Why? Because as I said, the features are very, very large. They are in basin scale, sometimes even at the same time in different basins. Another implication is the concept of water masses, because the water masses have been controlled and they are controlling the concept of the accommodation space in the water. And that is why you can see in many areas very large lateral migration of the deposits. As this example from Argentina, from Adam Kirby. Another implication are, as you heard before in palexonography, paleoclimatology, but there is something interesting that you should know based on this recent paper from Charu-Yin, is that on contours, especially on the drift, where the current is weaker, as I said, you can preserve higher percentage of organic matter, more than in other the water system, as pelagic sediment or as turbidites. And that is opening a very interesting aspect for future. Other implication, as you heard, geohazard, environmental integrity, ocean policy, energy design, and mineral resources. Normally, in this talk, one of the key questions is, have anybody drilled a contour system, or has anybody found any, reservoir or a field on this system? And the situation is that there are many samples from turbidines, and many, and more every year in mixed system. And the potential for the contour is there. And some of the mixed system, or that people consider mixed system, could be considered as contouritic as well. So the answer is yes, as far as you have, good reservoir, accumulation of sand, as you saw from the previous speaker, from Chris, and you have a good field, and you have, the condition to develop the field. Future consideration. Well, here you have this fantastic 3D block from Andreas Lake from the Gulf of Mexico. And you can see mainly two surfaces. One is around 1 kilometer deep, another one is in the present day surface. And analyzing this older surface, you can see the main feature in the seafloor by that time were gravitational, submarine canyons, submarine fans, after deposits. So we can really decode from these morphologies and from the distribution of the feature that for that particular time, the margin was mainly gravity driven. But you compare with the feature today in the seafloor, is really the opposite because most of the features are parallel to the margin. You can see furrow, channel, etc., that they are all trending parallel. So this is to remember, Sarah said, when the processes are not related. Sometimes this interaction of these processes are desynchronized, like here in the Gulf of Mexico in this example, but other they are synchronized. And I think now, today, there is a growing recognition that processes interact and the whole in the deep sea having that section. So that means that the common is the interaction of processes most of the time. That is why the complexity of the sedimentary fossils. A future consideration, I will highlight several. Contours and also meet the positional system are critical deep ocean features. They are based in scale. They are under-recognized, but they are omnipresent. And there is a simple reason because that is because the ocean today and in the past always have been in movement, always have been affected by processes. And we have to be in the situation to decode and identify these processes. This feature have an expanded sedimentary record, and this is useful for some reserve line. Very high stratigraphic significance. We started to know that through time, this contrast system and this system are especially in a specific time interval. And something that for me, this is the last, very important, the tectonic aspect of this. There is a close link between the onset, the growing, and the end of this depositional system with tectonic, and also with the evolution of the gateways. So here you can see this example for the Cretaceous. In the light blue, you have the opening of the gateways, and in the light orange, you have the closing of gateways. And the opening and the closure of gateways have been the key to have changes in the structuration of the water masses in the past or through time. What does that mean? That means that every time a gateway was open and two oceans started to be connected, you have probably a new water mass affecting to a new part of the continental margin, and therefore you started to have continuity feature there. And in some point, this feature stopped because there is some tectonic changes and also changes in the gateways. So in a recent publication that is going to be online in 3 weeks, we have compiled since the Jurassic to the Quaternary the evolution of these gateways. And it's quite interesting. I'm going to go just to the general aspect of this compilation. And the general aspect is that in the upper Jurassic to the upper Cretaceous, the circulation was mainly latitudinal, because the main gateways were more trending east-west. Not only, it's a simplification, but mainly. And then there is another period with many changes because of tectonic in the gateway that is mainly from the Middle Eocene to the Quaternary, where the gateways mainly were trending north-south. And then it's more a latitudinal, longitudinal, I think I said wrongly, longitudinal at the beginning and then now latitudinal connections. And this is very important, not just because, as I said, the onset of new water masses or changes in the stratification. This is very important because that affected or was one of the factors controlling the global climatic condition on our planet. Here you can see that the first period is mainly affecting the warming condition in the Cretaceous. And in the second one, you can see that is mainly controlling the colder condition in our planet. And another implication is in some of the hypotheses for the source-to-sink theory that is not considering the influence of water masses and oceanographic processes in this model. So, as I said, most of these deposits are along the slope and continental rise, and in those drifts, in those condritic systems, there is the store of a lot of sediment that they are not getting the deeper. So that is why contrast and mid-depositional systems are a new paradigm for the water sedimentary environment, because from my view, the better knowledge of this system are changing our model, are changing our mind. And for me, the key message from this talk is that we need a shifting mindset to fully understand the influence of these water masses, oceanographic processes in the water setting. And we have to include the drift in future models. And for that, it's not just academia, we need the collaboration from academia and industry. Our group is having a consortium with 11 companies, and it's going pretty well. We are all going the flow, and you want to go also with the flow, please join us. We are looking for industrial partners. And that's it. Just to remember, as you saw before, that we are organizing the BOMA sequence in Morocco. So please stay tuned because more information will be soon. And that's all. Thank you very much for your attention.
Thank you, Javier, for a really great talk, and I also want to just thank everybody. I know we're a little later than planned, so I really thank all the presenters for taking the time to present this incredible work. I think there was a fantastic range of work there. Really thank you to everybody for hanging on as well. Again, there's a lot of interesting questions, so what we're going to do, for the sake of time, because I know everyone is busy, we're going to take those questions. We'll make sure to send them to each presenter, and then we'll have the presenters answer them, and we'll work to get the answers out via email. But I just want to take a quick, essentially minute or two to summarize. Also, I guess we're recording this too, so that'll help to summarize that. Before finalizing though, very much thank you to SCPM. Thanks, Cassie, for helping organize all this. And really, again, a lot of this work was driven by Emma and Lillian and Stan. So very much thank you to everyone involved there. But I think the thing that I just want to really summarize within about a minute or two is, again, the importance of integration. And this is the same point, Javier, you just ended on. We had a great range of talks today. We only had 6 presentations, but I think both a clear story and a clear need are merged. Right? It focused on highlighting the complexity of deep water systems beyond what our traditional models have kind of placed together, right? And also the importance of integrating insights to improve our understanding and guide our decisions on that. So if you look across all of our talks, we discussed the range of processes operating in the deep sea. We talked about internal waves from Elda, and Javier discussed a series of the processes as well. Kevin then provided some valuable insight on understanding the spatial distribution as well as the interaction of these. I think it was really interesting how then Jürgen challenged our conventional views by demonstrating that, first of all, mud behaves very differently under deep sea conditions, and understanding that changes what we think about some of these drifts being developed on. Also, Kevin further emphasized the point that Jürgen was making about how frequent some of these currents might be, even though that might not be the most evident from sand deposition alone. So we've got to consider the mud fraction as well. Building on that foundation, Elda, Javier, Sarah, they kind of brought these processes together, used observations to refine some conceptual models of mixed contourite depositional systems. And I think Kevin spoke again, delivered both a synthesis and a challenge, right? Linking processes and products and developing very clear recognition criteria that help us differentiate those spectrum of deep water deposits. And I think what was really nice is Christoph, I think, demonstrated an impressive integration of how taking all of these concepts and regional data can actually help drive exploration, interpretation, new ideas in a pretty well understood system already. And so I think together across all those talks, it really showed that understanding the individual processes recognizing the products from those processes and integrating that within a process standpoint is key to developing our understanding from a scientific perspective, but also from a practical application and development context. So again, I just wanted to do a quick summary. Fantastic presentations by all the presenters. So thank you for that, and thank you for everybody that participated in this in terms of both questions and just showing up. So thank you to everyone, and thanks again, Cassie and SCPM, for helping us with this.
Of course. We did have a couple of questions about will the recordings be shared, and yes, they will.
So thank you. So we will send out an email blast when all those recordings are available, when the questions are available and answered as well. And we'll also follow up with additional polls. Thank you.
Fabian, can we have the screenshot for all of the speakers?
If the speakers are still there, yeah.
No problem from my side.
Thank you.
Yeah, fine for me as well.
Everybody turn on their cameras. Awesome. I will have my screenshot mode ready. Oh. I think Jürgen might be out. No, yes,
Quite
we got
Quite the rogues gallery, huh?
Yes, beautiful.
it. All right, one quick second. All right, 1, 2, 3. Oh, all right, perfect. All right.
Everyone say Contarite. Yay.
Yeah, exactly. No, thank you to everyone. That was honestly a real good mix of presentations. Those are fascinating.